Um, well, good evening. Thank you very much for coming. My name is Juanjo Madrigal. I'm a mathematician. I'm a software engineer currently working at Divo. And today I will talk to you about persistent homology. This is a relatively recent machine learning technique. It is quite complex and it is difficult to explain in 25 minutes, but I'll do my best. And it is being so successful in so many different areas that, well, at least it is worth a try. So, this is the most important question. Where is persistent homology being used? And, well, as an example, I bring you here an article that appeared in journal Nature in February 2019, which is about, persistent homology used to estimate the progression of prostate cancer. It was in the 1960s that a pathologist called Donald Gleason described a grading system to classify the evolution of prostate cancer. And the stages that he described were mainly geometric characteristics. I mean, in terms of the shape and distribution of cells in the cancer tissues. And, well, it may seem like an easy task, but when one gets to real examples, it is not so easy. So it is difficult for us. It is difficult for trained physicians. And if it is difficult for trained physicians, let alone a computer, it is quite hard for a computer to classify these tissues. But indeed, it has been done. And in the paper, the researchers explain how persistent homology was used to ease the process of classifying these cancer tissues. But it is not only for this prostate cancer that it has been used. It has been also used to study lung diseases, identifying obstructive patterns. It has been also used in neurology to study a certain type of cells in the brain that are in charge of mapping our movement, our position while we're moving in our environment. It has been used in biophysical chemistry to understand some molecules. It has also been used to model language learning, and also in material science, and in many other fields, more and more. So now we're ready for the second question, which is, well, what is actually persistent homology? And, well, let's start at the beginning. What is unsupervised learning? I will do a very, very quick review. So, how many groups, how many clusters do you see here? 3. Okay, nice. So, well, you know unsupervised learning. Congratulations, you did really well. Well, no, just kidding. I mean, yes, there are 3 clusters, but it's not so easy for a computer to tell us. We would like to have algorithms. And as for the 3 clusters, well, it is indeed not so easy. It may become quite unclear sometimes, because if the points are very scattered, then you don't know if you have 3 clusters or 1 big cluster. So perhaps the algorithm also has probably a hard time doing this task. Well, but hey, there are some algorithms that make this task, and they do it quite well. For instance, we have k-means and dbscan and many other algorithms, each one with its own properties. Nice. So, well, okay, well, what do you see here? It may seem like I'm conducting a Rorschach test, but it's not. So, yes, it's like a circle, like a ring. So, yes, it is easy for us, but we would like a computer to tell us about it. And as before, well, this may become quite unclear. It is not very, I mean, there might be noise in this process. And, well, there seems to be no very popular machine learning algorithm that is in charge of that, but persistent homology comes to the rescue. And where does persistent homology come from? Well, it comes from math, more specifically from a branch of mathematics called topology. And, well, what about topology? You know, perhaps you don't know about it, but in math, there are many things that start from other things that don't work. And topology is no exception, because I think we all learned in school a formula that said that in a polyhedron, when you add vertices plus faces minus edges, then it is equal to 2. And yes, it's a very nice formula that we all learned. It just doesn't work if the polyhedron is weird enough. And this polyhedron is weird because it has a hole in the middle. It's like a donut. So it seems that there must be something funny with this weird shape. There must be something that makes this formula don't work. And these kind of things that nobody cares about and that has no reasonable practical use is what mathematicians like the most. So as it seemed very curious to them, the mathematicians of the 19th and 20th century began to study it and to understand it better. During decades and decades, they studied and they created tools to work with it. And after that, some 150 years later, in June 2013, a kid called Juanjo Madrigal receives an exam in which he's asked to compute the homology of a pyramid of square base. And this kid, who is me, starts to fill a lot of formulas and computations to show that he has studied the subject properly. My algebraic topology professor was very happy indeed. And yes, this homology is studied within the subject of algebraic topology. The aim of this exam was not to test our calculus skills, but to show that we had some knowledge about how things work. And yet, this exercise already shows that homology has a characteristic, a feature, that is not at all common in pure mathematics, that homology is actually computable. So, well, it happens that homology comes like in two flavors, in two versions, that are like the two sides of the same coin, singular homology and simplicial homology. Simplicial homology is computable. It takes a space, triangulates it, and then makes some calculus based on the pieces that it has created. Singular homology, on the other side, is like smooth and flexible. It works with curves and with lots of other shapes, and it's infinitely more complex than simplicial homology, but it is the one that makes geometric sense. All the calculus that we make with simplicial homology can be seen, can be interpreted within singular homology. And that's why even when we could take many different triangulations and the calculus in between would be different, the results are always the same because the singular homology is always the same. Okay? So, I mean, these are like the two variants. One is very comparable, the other one makes a lot of sense. It is always said that singular homology looks for holes, but more than the concept of hole, it works with a key concept that is boundary. For instance, here we have a hole surrounded by a curve, but this curve, we don't want the curve to have boundary. In this case, the curve is not closed; it moves freely, so it is no good. It is open; it has two boundary points. But we also don't want that the curve is filled. I mean, in this case, we want the curve to go around the hole. We don't want it to be filled. this second circle is filled. It is the boundary of another circle. So the homology has a very clear motto: look for something that has no boundary and that is not the boundary of something else. And this may seem like it is a play on words, but it works. It actually works. And when we do all the computations, we find a series of features that are arranged in structures called homology groups, H0, H1, Hn, which are like holes in dimension n, so to say. H0, the homology group of dimension 0, counts all the connected components of my shape. H1 counts flat holes, and H2 measures hollow surfaces. All this very much quote unquote. In the other hand, the translations of all these geometric concepts to our computable scenario could not be easier. I mean, all these edges, triangles, tetrahedra, we may represent it with the list of vertices that delimit them. And in this context, the boundary operator, and it is operator because we have moved to the world of algebra, well, computes all the faces that are around it just by, well, taking all the combinations of removing one vertex. So it is algorithmically something very direct. And well, with all this data, one builds matrices, and then one computes all these homology groups that gives useful information. So when we want to compute the homology of a space, we take a space and triangulate it. So we go from continuous to discrete. But ironically, in our case, we want to do the other way around. I mean, I have a cloud of points, and then I think it comes from some underlying shape. I'm going from the discrete to the continuous. So how can I do that? Well, we will do the following. We have all the points, and then we'll add some matter. We're going to inflate the whole building. So in each point, I will put a circle whose radius is going to grow. And then whenever two circles overlap, I will put an edge between the centers. And when three circles overlap, then I have all the three edges. Then I'll put a triangle. And when I have 4 points that all the circles overlap with all the edges and all the triangles, I will put a tetrahedron. So with this, I'm building a shape, a triangulated shape, that is resembling the distribution of points. And I'm going to calculate the homology of these spaces. The space changes, and the homology changes. Here, I'm going from a bunch of isolated points to a very big blob. But in between, it is supposed to be topologically interesting features, like this ring that is formed. And just as a singular homology justifies that all the triangulations work great for computing homology, it also justifies that this method is robust to noise, that it doesn't change a lot by altering the points a little bit or changing the radii a little bit. And I will also look for those features that last for some time. That's why I say persistent homology. The most predominant features will be those that appear early and disappear later. And for those pictures that were like more scattered, then their features will appear later and disappear soon. Okay? And well, that's all very good, but we may think that computing all the homology for all these spaces that are continually changing, this would be something computationally exorbitant, something very difficult to do. And it would be right if it were not because homology, as I have said, is a very rich theory. It may be considered one of the richest and most successful theories in pure mathematics, as well as one of the most beautiful ones. And it knows how to handle spaces that grow, both in the geometric sense and in the computing sense. What this means for us is that we will be able to compute all this homology incrementally in something that is actually feasible. And I would like to give like an overview of how is the homology algorithm, very roughly. I won't go into much detail because we would run out of time, but you'll see that it is not so difficult conceptually, so to say. So, well, we'll work with a very little example, like these 4 dots. Some of them are closer and some of them are more far apart. And first we add the top edge, then the right edge, the bottom edge, the left edge, and finally the diagonal, which in turn adds 2 triangles. So what we will do is to take a matrix in which we will put all these elements. First, the 4 points in order of appearance, then the 4 edges, the diagonal, and the 2 triangles. And we will mark the boundary of these elements. The points have no boundary, but each edge has a 2-point boundary, and each triangle has 3 edges as boundary. So that's the first step. And then we will do a series of column transformation that will try to isolate those characteristics that are more interesting topologically. And this will be much like Gaussian elimination in matrices. And this transformation will be governed by a rule, which is that, well, for each column, the last cross will be a pivot, and a pivot cannot have other pivots to the right of it. So after the reduction, the matrix would be like this after 3 or 4 steps. And well, we see that there are many elements that have changed. For instance, the left edge has become the whole circle that has no boundary. This is interesting because it means that the reduction actually has been able to identify those something that is interesting for us. So when we have the matrix already reduced, we have all the elements for computing the homology. We just have to interpret it. So there will be a homological element for each column that has no boundary, because that's what we want. And it will survive until it finds a pivot in its row, because the pivot is the one that marks that it is the boundary of something else that has appeared. So for instance, here in our example, it would be like this. For instance, in H0, we have a point A. Point A has no boundary, and it also lasts until the very end. Remember that we said that H0 was measuring the number of different connected components, and here we have a component. So that's great. And we also see that point B, yes, it also doesn't have any boundary, but it doesn't last until the very end. It disappears really soon. And why is that? Well, you see, we're adding H, A, B. So in the beginning, A and B were distinct components. So they reflected in H0. But when HAB appears, they're no longer distinct components. They're connected. So point B disappears to imply that point A will represent both A and B. And with the other points, it is also the same. They disappear when the edges are being added. But besides that, we have something very interesting. For H1, we have a homological element, which is the whole circle. And well, as we can see, it appears when the left edge is added and disappears with the diagonal and the two triangles. So we have at the end a sort of barcode with all the homological elements for H0, H1, and whatever else. And each element has its own starting and ending moment. So when we apply this algorithm for a slightly larger example, we see that, yes, in H0, we start with a component for each one of the points initially in the cloud, but they disappear when everything joins together. So all disappear except but one. But besides that, there may be other elements that may appear. And for example, in this cloud of points, I see in H1 that a big bar is formed, which means that the dots actually are something like a ring. So what do we have in the end? Well, it's like we get a kind of barcode that is like a low-dimensional representation of the geometry of a cloud of points. So where we're conducting a machine learning study, we may apply persistent homology to extract the geometric information in a low-dimensional representation and then pass it to some other classification algorithm, like a support vector machine or a neural network or whatever we want. So, well, for instance, in these cases, in this first case, when the points touch, all the components disappear except but one, and there is a circle that appears and lasts for some time. In this other example, well, when the points touch, yes, also all the components in H0 disappear, and there are like 4 little bubbles that last very little until the diagonals of the squares are added. Here, for instance, you may see also a similar context, but and there are also like 2 small bubbles that are formed. But besides that, between the beginning that are like 8 isolated points and the end that would be a very big clump, there are two very differentiated groups, and they may also there might also happen that there are no significant homological elements, like in this case that is basically like a line, so nothing very interesting in this sense. And what happens when we have dots that look like textures, that look like tissues? Well, in cases like this, when the points touch, all the components disappear very soon, all but one. And there may be also very little bubbles, very little circles that appear, that also disappear very soon. But even in this case, even when components and bubbles disappear very soon, the proportion of the half-time of these lives may be different. And for instance, in this case, the bubbles live comparatively a little longer than in the first case. So this persistent homology is able to distinguish these two textures, is able to actually quantify the geometric nature of these textures that may be very useful for other for all the cases that we had seen in the beginning for these cancer tissues and so on. Well, I would like to end with a little touch of humor. This is a fragment from a conversation I had with a workmate in which we were joking about how fun it would be to give a talk that was blatantly abstract and mathematical. And well, it is a temptation that we usually have. But I think here the challenge was well, to do something that was entertaining, that was enlightening, and to show that, well, there are great ideas that come from combining tools in different areas that may be far apart. And I hope I have achieved it a little bit, and that you have liked it. And that's all. So thank you very much for coming.